Welcome all of you to this episode of October episode of Astro Adda. Myself, Jan Ganguly, is welcoming you, all of you, and we will be officially, actually, we will be welcoming you in a formal way by our Binoy Dubey, who is the in charge and the project coordinator of this center. So, Binoy sir, please, you can welcome.
Thank you all. Thank you, Mr. Gangopadhyay. Good evening, all. Thank you so much for being here. This is our 6th episode in Astro Adda, and today is the interesting subject, that is gravitational lensing of gravitational waves. I'm not expert in astronomy and all. First of all, I'm getting this topic. I am a little bit astounded at gravitational lensing, what is all about and all, because lensing here is I have heard it in the mirror or lens, something like that, because we know that normal lens, right? In the normal lens, we use the magnifying glass and pair of spectacles and work by bending light rays that pass through them in a process of refraction and then pointing to somewhere else, even such as in our eyes. And here we are talking today is the gravitational lensing. I mean, that is analogous, what I heard, what I have gone through. It is an analogous way that is having the effect of Einstein theory of relativity, that mass bends light. That is the thing. That gravity, we know gravity. We can say in a gravity that gravity is the curvature of space and time produced by mass or energy, something like that. And light, which we know travel in a straight line, now follows the curved space time, which is not at all a straight line, and that what we have seen in Eddington's observation. So in 2015, I think that scientists have just detected the gravitational waves, and these waves have created a merger of two black holes, and that at a distance of 1.3 billion light years away. So the waves were existing for a small period of time, and now here we are today discuss about this gravitational lensing of these gravitational waves. So friends, today we'll discuss all these things, all the different aspects. I welcome Mr. Ajit ji, who is there in our August presence. Welcome, sir. And please, I think that viewers are very much eager to hear about this gravitational lensing. This the new subject, I think, emerging in astronomy, as in greater impact to explore the dark matter, dark energy, black holes, etc. So over to Mr. Gangopadhyay. Please carry on. I am interested also to hear all these things. Let the Adda begins.
Thank you. So this Astro Adda is a joint program between Regional Science Center Calicut and Public Outreach and Educational Committee of Astronomical Society of India. We do it for last 5 months. We are doing it every month. One speaker comes and speaks about it. So before we go into today's talk, actually I will just introduce the speaker to all of you, so that after that we can hand it over to the speaker. So Ajit Parameswaram is currently Associate Professor at the International Center for Theoretical Science, TIFR, Bangalore, where he leads the Astrophysical Relativity Group. His research spans various aspects of gravitational wave physics and astronomy, including theoretical modeling of astrophysical sources, gravitational wave data analysis, and observational test of general relativity. Ajit has been a Ramanujan Fellow, a CIFAR Azirelli Global Scholar, and the head of Max Planck Partner Group on Astrophysical Relativity at ICTS. As a member of LIGO Discovery Team, he is the recipient of 2016 Special Breakthrough Prize in Fundamental Physics and the 2016 Gruber Cosmology Prize. Recently, he was awarded the TWAS-CAS Young Scientist Award for Frontier Science by the World Academy of Science. So Ajit, the dais is yours now, and we are eager to hear your wonderful talk. Please, yeah.
Thank you, Jayant and Dr. Dubey. Before I start, I wanted to thank the Regional Science Center, Calicut, and the Astronomical Society of India for inviting me to this public lecture series that has been going on quite well for the last several months virtually. I've had the good fortune of going to the planetarium in Calicut, I think soon after the LIGO announcement of the detection of gravitational waves in 2016, and I had a wonderful time talking to a lot of very enthusiastic students and interested public at large. So I'm very glad to be back talking to many of you again. So as we have heard from the introduction itself, Dr. Dubey has sort of stolen my punchline already. So most of the things that I wanted to say has been said. So just like we see lenses and magnifying glasses normally in our daily life, it turns out which basically focuses light through a process called refraction. It turns out that very massive object can also act as a lens by bending light. And this is because these massive objects curve the space-time around them, and light, while traveling to the straightest path possible in the curved space-time, will eventually take curved paths. This was predicted by Albert Einstein's theory of general relativity, and was subsequently verified in the first half of the last century by a remarkable astronomical observation by Arthur Eddington and colleagues. And I will start from the beginning, and eventually today's talk is sort of focused on not necessarily on the gravitational lensing of light, which has been around for more than a century now, but about the gravitational lensing of a different type of wave, so-called gravitational waves. And it turns out that the gravitational waves will also be bent and lensed exactly in the same way as light, which is not yet observed. But there are good reasons to believe that we will observe the first signatures of the gravitational lensing of light in the next few years, which a lot of us believe that will be a completely completely new and powerful new way of probing the astrophysics. So that would be the gist of today's talk. So let me start from the beginning. The prediction that gravity bends light as well as gravitational waves come from the general theory of relativity that was proposed by Albert Einstein in 1915. And as most of you know, this is the most accurate description of gravity that we have right now. And this is a very dramatic departure from the earlier description of gravity that was due to Isaac Newton, which describes gravity as a force between massive objects. Here in Einstein's theory, gravity is described as the curvature of space and time. And any massive object, including Newton's apple, as well as other forms of energy, for example, electromagnetic fields, for example, would produce a curvature in the space and time. And this can have a number of very interesting consequences. So, for example, just like an apple, a sun would also produce a significant curvature in the space-time around it. And the light that would usually travel through a straight line would start traveling through the geodesics of that space-time. Geodesics are the curves that are basically the shortest paths between 2 points. And in the case of flat space, the geodesics are straight lines. That's why light travels through straight lines in our daily experience. But if there is a significant gravitational field and the space-time is curved, then the light will travel to the geodesics of that curved space-time. And here is a concrete example of something that one could actually observe. Here there is a star, a distant star, whose rays are grazing the limb of the sun. And because the space-time is curved, the path of the light is also curved. And an observer who is looking at from the other side of the sun, for example, the Earth, would see a shift in the apparent position of the stars. And this can be calculated because if you know the mass of the sun, and it turns out that it is a small effect, but potentially measurable. And so one has to actually wait for a solar eclipse for making a measurement like this, because you cannot see stars during the day near the sun. So this is what was done by two teams of astronomers led by British astronomer / physicist Arthur Eddington during a total solar eclipse of 1919. And a couple of years ago, we celebrated the centenary of this remarkable observation by Eddington and his colleagues. And the right side shows an actual photograph taken by Eddington and colleagues from this eclipse, and you can see the solar corona. And if you look very carefully, you can see stars, which is not very visible in this photograph. Remember, this was more than 100 years ago, and the astronomical photographic techniques were quite primitive. But here is a cartoon version of what Eddington and colleagues have observed. So what they have done is to take a photograph of these cluster of stars from the Hyades cluster during the eclipse, and that is shown by these red stars in this photograph. And after a few months, when the same cluster of stars appear in the night sky, when there is no sun in between us and the stars, then they have taken another photograph. This is called a reference photograph, and that is shown by these blue stars here. And you can see that the relative positions of stars have shifted during the eclipse because of the presence of the sun in between us and these distant stars. And you can see that the closer the star is to the limb of the sun, the larger is the shift in the angular position during the eclipse. And the typical shift is of the order of an arc second or so, quite small, but it is still possible to measure it. And comparing it with the reference photograph, one could actually measure the apparent shift, which was found to be consistent with the prediction of Einstein's theory. Because one knows the mass of the sun, one could actually calculate the curvature of the space-time produced by the sun's gravitational field, and can calculate the shift in the expected shift in the position of the stars. And the observations were found to be consistent with the prediction of theory. This was perhaps the first remarkable observational test of this completely new theory of space and time, as well as gravity. And this was celebrated across the world. So, for example, the right-hand side here shows the headlines from the New York Times. And this very emphatically says that Einstein's theory triumphs, and the stars were not where they seem to be, but nobody need to worry. This was celebrated not only in the Western world, but across the world practically. So here is the left-hand side shows an article appeared in the Statesman newspaper, published from Kolkata. And this article was written by no one other than Meghnad Saha, in which he makes a very prophetic statement that if these observations by Professor Eddington's hold, then our understanding of the space and time would completely change, would undergo a revolutionary change. And this is what indeed happened in the last century. Our understanding of space and time indeed underwent a major change. And now these sort of gravitational bending of light, as well as radio waves, etc., by the sun, has been verified with much better precision in the later decades of the 20th century, especially using radio astronomy. And now these sort of much more dramatic versions of these gravitational bending of light, which is now called gravitational lensing, is a very commonplace phenomenon in modern astronomy. In fact, now that we believe that we understand the theory of space-time and the theory of gravity, we can actually use these observations of gravitational lensing to probe unseen matter distributions in the universe. And it has indeed been emerged as a very powerful probe to probe things like dark matter in the last few decades. So here is one cartoon version of a strong gravitational lens. So there is here is the Earth. We are on this left side, and there is a distant galaxy, and there is another galaxy in between us and this distant galaxy. And this galaxy, the middle galaxy, acts as a gravitational lens by bending the space-time around it. And this means that this light from the distant galaxy can basically reach Earth through different paths. And eventually it can produce multiple images of this background galaxy. And this is called a gravitational strong lensing, if there are multiple images exist. And so here is this is while the earlier image was is a artistic impression. These are some real photographs of the gravitational lensing in action. The left image shows what is called a gravitational strong lensing, and this shows the radio image of a distant quasar. Sorry, I think this is an X-ray image, not a radio image. I'm not entirely sure. But anyway, you can see that these are four images of a distant quasar, and basically there is only one object, and because of an intervening galaxy that comes in between us and this distant quasar, it forms four images of the same object. And so this is an example of what is called a gravitational strong lensing, which basically not only magnifies an image but also produces multiple images of the same object. And the middle example shows an example of what is called the gravitational weak lensing. This is a photograph taken by the Hubble telescope. Here, the density of the gravitational lens is less than a critical density, so it does not produce multiple images. But by bending the space-time around it, it basically introduces characteristic deformation in the shape of the background image. So you can see these arc-like shapes, which is a telltale signature of the gravitational weak lensing. And this also can be used to map out dark matter distribution in the universe, etc. The right example is an example of a gravitational microlensing. Here, the lenses are typically much smaller, and it must so that there is no possibility of making multiple images or even significant deformations in the background images. But if there is a relative motion between the lens and the source, then this microlensing can produce a time-dependent change in the magnification of these distant source. So here is a cartoon example. Here is one has to look at, this is a time running from left to right. And there is a distant star here. And there is a compact object, which is codenamed Macho, in between this star and us. And because of the relative motion of the star and this compact object, when this compact object comes in between us and the star, then suddenly you see an increased magnification of the starlight. So here is an example of how the magnification would change as a function of time. And this is a signature of a gravitational microlensing, and it is observed routinely, and in fact this has been used to detect things like planets outside the solar system. And in the last few decades, gravitational lensing of light has emerged as a powerful tool for astronomers and cosmologists. And the examples of these power of these probes include, these have been used to, gravitational lensing have been used to probe, to identify, to find evidence of dark matter, and to map out dark matter distributions in the universe, to understand the nature of dark matter, for example, to understand to check whether the dark matter could be comprised of a large number of compact objects. Just like a normal magnifying glass, which would amplify the light and produce a more intense image, one could actually expect that the gravitational lensing would also magnify distant objects and can be used as a magnifying glass to look at very distant objects. And there are examples now where we have seen stars from millions of light years away, which would not have been visible otherwise, but just because there was a galaxy in between us and this distant star, which would magnify these signals, the starlight by thousands of times. Astronomers have observed some very distant stars, etc. So there are some really cosmic magnifying glasses in action. So here are some example images that shows the power of gravitational lensing in action. So I'm not going to describe these in detail, but if there are questions, I can come back to this at the end of this talk. So gravitational bending of light is only one of the many interesting predictions of Einstein's theory. Einstein's theory has predicted a number of very interesting predictions. For example, the gravitational time dilation or gravitational redshift, existence of black holes, expansion of the universe, etc. And all of these predictions have been verified with really remarkable accuracy by a number of astronomical observations as well as laboratory tests, precision laboratory tests in the last few decades, in fact, the last century. And the one prediction that was directly verified very recently is the existence of gravitational waves. Gravitational waves are also produced by massive objects in the space-time, moving with very large velocities. So for example, this is again an animation, but it's a purely artistic impression that shows how the space-time curvature would change when two massive objects, like two stars, would move around each other. So basically, when we discuss that a massive object would change the curve of space-time around them, and when they move, the space-time curvature basically follows them, and this creates disturbances in the space-time that propagate at the speed of light. So these are called gravitational waves. So gravitational waves are nothing but oscillations in space-time geometry that propagate at the speed of light. We have had indirect evidence of the existence of gravitational waves in the last few decades by the radio observations of binary pulsars. But in the last 5-6 years, we have been observing gravitational waves from colliding compact objects, neutron stars or black holes, producing very strong gravitational waves which pass through the Earth. And using Earth-based gravitational wave observatories, one can actually detect them. And indeed, in the last 6 years, the gravitational wave observatories LIGO and Virgo have observed dozens of such gravitational wave signals produced by collisions of black holes or neutron stars in different parts of the universe. So here is a cartoon version of the sources of gravitational waves detected by LIGO and Virgo over the last 6 years. So all of these signals are produced by mergers of compact objects involving a neutron star or a black hole. So these are binary systems, and these objects move around each other with very large speeds, producing very strong gravitational waves. And they lose energy and angular momentum into gravitational waves, and they come closer and closer, and eventually collide with each other with very large velocities, forming a much more massive compact object. Most of the time, that new form compact object is a black hole. And so that's why, for example, one merger basically involves three compact objects. You start with two compact objects that would form a third, more massive object. And here is a zoo of all these compact binary mergers that were detected by LIGO and Virgo. So here is, for example, two black holes that have masses of the order of 20 and 25 solar masses merging to form a more massive black hole of the order of 40. And all these blue dots are the black hole mergers detected by LIGO and Virgo. And in comparison, we also show the black holes detected by X-ray observations from our own galaxy as purple dots. And you can see that the LIGO-Virgo black holes are on average much more massive than these black holes detected by X-ray astronomers from our own galaxy, which was a bit of a surprise for most of the astronomers. But it is not anything completely extraordinary also, because these LIGO-Virgo observations are from very, very distant galaxies, potentially formed from in a much earlier universe, etc. So here also, this plot also shows the neutron stars detected by LIGO and Virgo as orange dots, and in comparison with the binary pulsars detected by radio observations in yellow. And again, since neutron stars also only have a very small mass range, they're not very different from the neutron stars detected by radio observations. So one point I would like you to notice is that in the last 5 years, like last 5-6 years, LIGO and Virgo detected of the order of 50 gravitational wave signals, but these detectors have not yet reached their design sensitivities, and their sensitivities are being improved now. With each modest improvement in the sensitivity, there is a significant increase in the volume that these detectors can reach in the universe, and there's a significant expectation that it's an expected significant improvement in the detection rate. So if you continue improving the sensitivity in the same way, in the next few years, we will be detecting thousands of gravitational waves in a matter of next few years. So we are really opening up a new branch of astronomy by the observations of these signals. And this is indeed a new branch of astronomy which have produced really remarkable science in the last 5 years. It's very hard to summarize this in one talk. So I'll maybe list a few very, very important points. So for example, these observations provided the first detections of merging black hole binaries and binaries of black holes and neutron stars. We had no direct way of observing these until now. These observations also have uncovered a new population of heavy black holes. I told you that most of the black holes that were detected from our own galaxy have fairly low masses, which is of the order of 10 solar masses, while most black holes that LIGO and Virgo have seen are much more massive than about 30 solar masses or so. We also have detected one signal which potentially provided a hint of an existence of intermediate mass black holes that are more massive than about 100 solar masses. And most remarkably, this one signal, gravitational wave signal produced by a merger of neutron stars, also basically inaugurated a new field called multi-messenger astronomy, because this signal, this merger that produced this gravitational wave signal, not only produced a gravitational wave, but also produced a burst of electromagnetic radiation, which was detected across the electromagnetic frequencies, starting from gamma rays all the way up to radios. So, and all these observations have provided some really powerful probes of fundamental physics. For example, the nature of gravity, some clues about nuclear physics at extreme densities, etc. Astrophysics, a variety of areas in black holes and neutron stars, and cosmology also, because we have now a new way of measuring the cosmic expansion rate from the observations of compact binaries. They also have uncovered new mysteries. So, for example, we know that these heavy black holes now exist in the universe, And I told you that this was a bit of a puzzle for most of the astronomers, because it is not entirely clear how nature produces this heavy black hole, and in particular, what is the precise astronomical mechanism in which nature forms these boundaries of heavy black holes is not clear. And it's a very active area of research, and it's a very rapidly expanding field, and tens of papers are coming up every day, and that are very, very interesting. And I would, it's very hard to summarize all the sciences, but I would especially encourage you to look at these science summaries produced by the LIGO and Virgo collaboration. So the LIGO and Virgo collaboration basically writes up, and whenever they put up a new paper that describes a new science result, the paper is accompanied by an accessible science summary, which basically discusses the main science that is supposed to be accessible to general public also. So these are, and you can look at this web page of the LIGO collaboration for these science summaries of the papers by the LIGO and Virgo collaborations. Okay, so in the next few years, as I told you, we are expecting the detection of hundreds to thousands of gravitational waves, and this is going to produce a lot of very, very interesting probes of different aspects of fundamental physics, astrophysics, and cosmology. I'm not going to read out this full list, but there are different aspects of black hole astrophysics, nature of strong gravity, extreme matter like nuclear physics in extreme conditions, cosmography, which is basically the field of measuring the cosmic expansion rate accurately, etc. That they are going to benefit hugely from this new window to the universe. Apart from this, these currently observed signals from compact binaries, we are also expecting possible detection of new types of gravitational signals by, for example, a stochastic gravitational wave signal produced by a large number of such astrophysical signals. Potentially a supernova from our own galaxy would produce a detectable signal. Rotating neutron stars producing what is called a continuous radiation of gravitational waves, analogous to the radio waves from pulsars. So these are all potential signals that we know should exist. It's sort of the known unknown. One could also speculate that one could also see some completely new unknowns also. And this is like a rough timeline of the gravitational wave observatories. In particular, we are expecting that the LIGO India will also come up in the next few years, which would contribute to the worldwide network of gravitational observatories, significantly increasing their science capabilities. So one such science capability that we are excited about is the observation of the gravitational lensing of gravitational waves. So, and here the physics is practically the same as light. According to Einstein's theory, gravitational waves are bent exactly in the same way as light by massive objects. So, for example, if there is a galaxy in between a gravitational wave source and the detector, basically this would curve the space-time around it, and there exist multiple paths that connect the source and the observer. So gravitational waves can pass through multiple paths and reach the observer, and can produce sort of multiple images of this source, exactly the same way as the example of these lensed quasar. So one interesting difference here is that the gravitational wave signals from compact binaries are transient signals. They last in the detector. They last only for maybe a second or a fraction of a second, up to a few seconds. This is very different from, for example, light from a quasar, which is there for a very, very long time. And the time it takes for these gravitational signal to reach from the source to detector through these multiple paths can be different. This means that one copy of the signal can arrive at one day, and another copy can arrive, minutes or days or weeks after the first signal. So in the case of gravitational waves, one could actually measure the time delay between multiple copies of the gravitational waves produced by these lensing. And another difference is that, unlike in the case of electromagnetic radiation, we cannot resolve this angular location of the sources in the sky very well. So we cannot see the images. We cannot make images of these sources in the sky. But what we can measure is actually a time evolution of the signal and their temporal differences of multiple copies. So within 100 years after the Eddington's observation of the gravitational bending of light, we are in the verge of detecting the gravitational bending of gravitational waves. The recent estimates have shown that a small fraction of these gravitational wave signals detectable by LIGO and Virgo in the next few years will be strongly lensed by intervening galaxies. And the probability is very small. It's just of the order of 0.1% to 0.5%. But because we will be observing thousands of events in the next few years, there is a statistical probability that a small fraction, a handful of them would be lensed, even in spite of the small probability. So how do we identify them? How do they appear in these detectors? Basically, the galaxies are these dominant gravitational lenses, and their gravitational radius is huge. They have masses of 10 to the 13 or 10 to the 12 solar masses. So their characteristic gravitational radius is very, very large, and the wavelength of gravitational waves is small as comparable to the gravitational radius of these galaxies. So basically, the whole problem can be thought of in terms of geometric optics, just like we do, lens calculations, optic calculations in geometric optics, in usual optics. And if you do that calculation, you would see that basically the multiple copies would practically look the same, except for a relative magnification and a time delay. So basically, the way to detect gravitationally strongly lensed gravitational waves is basically by looking at gravitational wave signal that look very, very similar to each other, that separated by time delays of minutes to days or weeks. But I told you there is a difference between the multiple copies, because the magnification seen by these multiple copies can be different, and in some rare cases this magnification can be extremely high, which means that these lensing would allow us to see very, very distant sources which would not have been observable otherwise. So if a signal is from a source to a very large cosmological distance, then the apparent brightness or loudness of the gravitational signal will be very small and too weak to be detectable. But if there is a strong gravitational lens in between us and the source, that would magnify the signal and render them detectable. And we have seen such examples in the case of electromagnetic lensing already. So here is an example of a distant star that is about 9 billion light years away, which is magnified by more than 2,000 times by a galaxy cluster that happened to be in between us and the source. It is unimaginable to detect a star at this kind of distances in the history of astronomy, but purely because of this accidental lens that happens that came between us and the star, this very distant star was observable. And lensing had allowed us to observe some very, very distant galaxies. In fact, the very first galaxies in the universe, etc. And of course, the probability of getting these extreme magnifications is very rare. But one could get magnifications of the order of a few and 10, etc., which would basically increase the distance reach of gravitational wave detectors. And there's an example of a study that shows how the distance reach is improved, etc. And interestingly, if you do not account for this effect of gravitational bending, this can potentially bias our mass measurements. So the idea is the following. You cannot tell apart a very, very bright source that is far and a less bright source that is very close, because their apparent brightness is very similar. So basically, lensing involves magnifying the signals. So basically, its apparent brightness increases. So we could actually mistake them for being a nearby source. And if the source is taken as a nearby source, then the cosmological redshift that we assign to this would also be very small. And it turns out that if you want to actually get the true frequencies of signals, you have to take out this cosmological redshift. And if you want to measure the true mass of this black hole that produces gravitational waves, one has to take into account this cosmological redshift also. So just to summarize, basically, if a signal is actually magnified, and if you do not know that, we would overestimate its mass. And there are people who argue that these heavy black holes that we have seen in LIGO and Virgo are nothing but gravitationally lensed signals. And this has been contested by most of the astronomers and physicists in the community, because if you take into account the standard astrophysical paradigm, this is highly improbable. But anyway, one could actually look for real convincing hints of the gravitational lensing of gravitational waves. For example, the observation of the existence of multiple images, like this case of this lens quasar. And here, what we need is to look for basically gravitational waves that look extremely similar to each other in the data set. And they could be separated by time delays of minutes to days or weeks, etc. And this is a much harder problem, unlike in the case of electromagnetic observations, because of the weakness of the gravitational waves. The signal to noise ratio that we are getting in the measurement of gravitational waves is very modest. As you know, it's very different from the electromagnetic astronomy. So one has to develop some fairly sophisticated statistical techniques, and one such technique is called Bayesian model selection. And in fact, our group has recently developed a way of identifying a way to identify strongly lensed gravitational wave signals in the gravitational wave data. And basically, this involves looking at a robust way of identifying signals that look very similar and come from the same location of the sky. That's the gist. And one could also use some other information. For example, the time delay between images will be determined by the nature of the lens. And we have an understanding of what is the major lenses distributions, because we have done large galactic surveys using electromagnetic telescopes. And we can make a prediction of the expected distribution of the time delay between multiple images in the case of a lens signal. And one could use this as a way of discriminating between truly lens signals and accidentally consistent signals. So basically, the problem is the following: if you take a pair of signals, gravitational signals in LIGO Virgo data, you can ask. There are two possibilities. One is that these two signals are lensed copies of the same gravitational wave signal, same merger, or they can be produced by, these signals are produced by two different mergers. So one could quantify this likelihood, the statistical likelihood of these two different hypotheses, and one could rank them and see if there is a significant evidence of the lensing in the existing signals. And such analysis have been done, and so far we do not see any significant evidence of lensing signatures in the gravitational wave signals detected by LIGO and Virgo. But again, if we extrapolate these calculations, there is a possibility of detecting the first lensing observations in the next few years. And unlike in the case of the lensing observations of light, gravitational wave observations observations of lensed gravitational waves can potentially probe new regimes of lensing. And this is one is called the wave optics effects. So this is sort of, here is, you can see an example of this, very familiar double slit diffraction pattern. So if you have two waves coming from two different slits, basically they would interfere and produce, produce interference and diffraction patterns. These are due to the wave nature of the light. And similarly, here, if the mass of the gravitational lens is, or the gravitational radius of the lens is comparable to the wavelength of gravitational waves, this is analogous to these double slit experiments of light. And you can actually see effects of the wave nature of gravitational waves by diffraction and wave optics effects. And this would, for example, introduce characteristic deformations in the observed gravitational wave signal. So here is an example of a plot. The gray plot here is a plot of the original gravitational wave signal produced by the merger of two black holes. And these red and black shows how the signal will be deformed if this was lensed by a compact object of about 100 solar mass and 1,000 solar mass. So you can see that they are quite different, and one could actually look for such deformed gravitational wave signals. Again, such analysis have been done, and the summary is that we have not seen any evidence of wave optics effects in the observed gravitational signal. And I'll show after the next couple of slides that even this non-observation of lensing can be very interesting probes of the nature of dark matter. Okay, so there are some very interesting observational, some observation that I claim to be very interesting. But why do we care? Why is this a big deal? So there are, just like the lensing of light has emerged as a powerful tool for astronomy, we hope that the gravitational, because that will give us some very interesting clues on the real nature of these black holes and black hole binaries. What is the astrophysical mechanism by which these binaries form, which is, as I told earlier, is an uncertain paradigm in this current astronomy. One could also use these lensing of gravitational waves to understand the nature of gravity itself, or the nature of gravitational waves. And here also the idea is quite clever, I think. According to Einstein's theory, gravitational waves have two polarizations, just like the case of light, electromagnetic waves. But and any single detector would measure a linear combination of these polarization modes. So this means that if you want to extract the two different polarization modes, one need to have two misaligned detectors, which would measure two different linear combinations of these polarizations, and one could solve for this in principle. In practice, it is much harder. But now there are some alternative theories of gravity, so alternatives to Einstein theory, which predicts up to many more alternative polarizations. For example, there are gravitational waves are what are called tensor modes in Einstein's theory, but there are theories that predict scalar modes, vector modes, etc. And if you want to now disentangle these two possibilities, you need to have many misaligned detectors, which we do not have. But the lensing observations provide a clever way of practically doubling the number of detectors by to observe a signal, because the idea is that if you think of just one example of one detector measuring a gravitational wave signal. So one copy of the gravitational wave signal was basically involves measuring one particular linear combination. But if this signal is lensed, its next copy would arrive after a few minutes or a few hours. And so if it comes a few hours later, then the Earth would have rotated, and the same detector would measure a different linear combination of the two polarizations. So basically, one detector allows us to measure these two different linear combinations. So you're practically doubling the number of detectors to measure the same signal. And this allows us to improve the ability to disentangle the polarization modes, and it's a powerful probe of the nature of gravity and the theory itself. Another very interesting measurement that the lensing can provide is to constrain the nature of dark matter. We know that the dark matter is a major puzzle in modern astronomy. We know that dark matter has to exist if you want to observe, if you want to explain the observations. And the precise nature of dark matter is not entirely clear. So most people believe that dark matter is some beyond standard model particles, while there are a lot of cosmologists who argue that dark matter could be comprised of large number of compact objects like primordial black holes. And if this is indeed the case, if the galaxy is filled with a large number of primordial black holes, then this means that these gravitational waves coming from us and from the distant source to us would be micro-lensed by these large number of black holes coming, appearing in this galactic halos. And if then this would introduce characteristic deformation in the observed gravitational signal. And if you do not observe such deformations, then one can actually constrain. One could say that the fraction of dark matter in the form of compact objects can only be less than some amount. And we have indeed done that recently. This is a paper that has been appeared in arXiv a couple of months before. And this shows that this known observation of these lensing signatures in the gravitational waves observed by Lyco and Virgo can be used to rule out that not all dark matter in the universe could be in the form of primordial black holes in this mass range of about 100 to 10,000 or 1 lakh solar masses. And these constraints are fairly modest right now, but with larger number of observations coming up in the next few years, one can actually put very, very significant constraints on the fraction of dark matter in the form of compact objects. So these are some example shows potential probes that will be enabled by, in fact, that are being enabled by the lensing observations or even non-observations of gravitational lensing of gravitational waves. But I want to sort of stress that we are only scratching the surface now. There are really, really new uses of the lensing observations of gravitational waves coming up as we speak. So let me stop here and summarize. The lensing observations of gravitational waves, the observations of gravitational bending of light was started as a way of testing the validity of GR by Eddington and his colleagues. But eventually it became a powerful tool for astrophysicists and cosmologists. And the story is similar to the case of gravitational waves. And now it has established as a new and a powerful branch of observational astronomy. And the first observation of the gravitational lensing of gravitational waves are expected in the next few years. So it's like a Doubly Einstein. So, this is not only an interesting observation per se, but it's also a powerful tool for astronomers and cosmologists. So we are hoping to see some real remarkable observations coming up from this new area of astronomy in the next few years. So let me stop here and thank you very much.
Yeah, thank you, Ajit, for such a wonderful lecture, and it was so insightful and so many new things we heard from you today, and many of the informations were actually fully new. We didn't know about it. And now is the question time. We ask all the audience to ask a lot of questions because it is an Adda actually. So we want a lot of interactions. And I think we will start with a few questions which are already in the board, chat board. You can either unmute and ask or you can put it in the chat board. So first question is by Kiran Mehta. She is asking, why cannot a simple explanation not be offered? Means I think why cannot a simple explanation be offered for intermediate mass black holes born by merger of low mass black holes? Something, yeah.
Right, yeah. So there is no problem with explaining the existence of intermediate mass black holes. In fact, this would be one sort of easy way of producing intermediate mass black holes. And in fact, this is what we think that has produced in this one particular merger that LIGO has observed through gravitational waves. These are involves mergers of two black holes, which is the masses of 60 or 70 solar masses, and the end product must have had a mass of more than 100 solar masses just by adding the masses and subtracting the energy lost into gravitational waves. So there is no problem in explaining the existence of intermediate mass black holes. One could still worry about some details. One is that, so the only question is whether we have seen and we do have a convincing observational evidence that such things happen in the universe. And so far, I believe the only very strong evidence is from the observation of these gravitational waves. There has been other observations in the past, like, for example, the existence of what is called these ultra-luminous X-ray sources, which was claimed at some point are intermediate mass black holes accreting gas and producing these very strong X-rays. But these arguments are being contested by other astronomers. So conceptually, there is no problem in the production of intermediate mass black holes. The only question is whether we have seen, we do have a sufficient observational evidence that these objects exist. Okay, the next question is also from Kiran.
Yes.
Yeah.
Why is a lens detection of gravitational waves or electromagnetic waves expected to be quadruple appearance rather than a whole ring? It's why it's not an Einstein ring or something like that.
Yeah,
like a four cross. It is a cross. So that's what I think is the.
Yeah. So sorry, I must have communicated this in an incomplete way. The precise nature of the image depends on the symmetries in all the problems. It depends on the geometry of the lens, the precise locations of the source with respect to the lens, etc. For example, if the lens and the source is precisely in the optical axis in the same line, then there is a cylindrical symmetry to the problem, and the image will be a perfectly Einstein ring. And so the number of images and the nature of the images depends on the symmetries, which involves the relative location of the source as well as the precise geometry of the lens, whether that is the lens is a point mass or a spherically symmetric or other symmetries, etc. And one example that I showed just happened to be a quadruple appearance. It does not mean that generally the gravitational lenses are have quadruple images. They come in all different shapes and sizes.
Okay. So, we have a question from Mohammad Sahil K. Can a supernova create gravitational waves?
Indeed, it is not necessarily the supernova explosion as such, but the collapse of the stars and production of the compact object at the core can produce gravitational waves. But in fact, the strength of gravitational waves is weaker as compared to the gravitational waves produced by merger of black holes or compact objects. So we can observe a gravitational waves from a supernova only if it happens in our own galaxy. This is what is shown by numerical calculations of core collapse, etc. And the supernova rate in our galaxy is of the order of 1 per 50 years. So one has to be a bit lucky to see a supernova happening in our own galaxy in the next few years.
Yeah. So we have a question from Adarsh Moha, which says that why it is difficult to localize the exact sky location of gravitational waves.
So basically, if you are using a telescope to localize a source of wave, basically there is something called a diffraction limit, right? So you have your angular resolution is basically given by the wavelength of the signal. And in the case of optical light, the wavelength is of the order of microns. That's why you're able to observe these, localize these optical sources very well. In the case of gravitational waves, the wavelength is of the order of hundreds to thousands of kilometers. So that is particularly, and so basically the lambda divided by the d, which is the size of the telescope, is the diffraction limit. And so in the case of the gravitational waves, the wavelength is of the order of hundreds, thousands of kilometers, and the d, which in this case is the separation between detectors, is also of the order of thousands of kilometers. So that's why our localization ability is of the order of few square degrees. In the case of optical light, that lambda itself is very small. It's like hundreds of nanometers, right? It's like microns. And if you have meter scale telescopes, that is 10 to the minus 6, that ratio. And that's why we are able to localize these optical sources much better than the case of gravitational waves.
Yeah. So somebody else, if you have any question, you can unmute yourself or put it in the chat box. Meanwhile, I will just, to keep engaged, I will just ask a question myself. You mentioned about something called an alternative polarization. Can you throw some more light on what do you mean exactly by alternative?
Right. So, in the case of gravitational waves predicted by Einstein's theory, the waves are what I call quadrupolar. They have tensor nature. This means that if you shine a gravitational wave on a ring of particles, one direction gets stretched and the other direction gets compressed. These are quadrupolar waves. But if you look up, for example, the polarization of light, right? If you have a charged particle, basically it just introduces oscillations in one direction. So these are called vector modes. And in Einstein's theory, these vector modes are absent. There are these, you don't, for example, if you have a ring of particles, you don't have and if you shine a gravitational wave, you do not see just this ring going to one direction. When the space gets stretched in one direction, it compresses in the other direction also. But there are theories that predict that this would also happen. So one particular polarization mode would just cause this space to stretch in one direction without causing anything in the other direction. So these are called vector modes. And there could also be called what we call a scalar mode, where the space expands in all directions the same way and compresses the same way. So these modes are absent in Einstein's theory, but there are alternative theories that predicts that gravitational waves should contain these other polarization modes also.
Thank you. So we have one more question by Mohammad Sahil. How gravitational waves are detected in the gravitational wave observatories?
Yeah, so there are different ways of detecting gravitational waves. The most successful one, like the only successful one so far, is the technique using laser interferometers. So basically, these observatories called LIGO and Virgo are what are called Michelson interferometers. They have an interferometer in the L shape. They have two orthogonal arms. And basically, they use a principle, the understanding that when gravitational waves go perpendicular to this detector, the space gets stretched in one direction and compressed in the other direction. This means that if you have an interferometer like an L-shaped object, the X arm of the interferometer gets longer. At the same time, the Y arm of the interferometer gets shorter. And interferometry is a way of measuring these relative length of these arms, because what it does is it basically shines a laser beam, and using two mirrors, it just reflects back. And if one arm gets longer, it means that this light beam gets longer to go and come back as compared to the light beam going in the Y direction. So one could measure the time delay between the round trip time of the light in the two different arms, and that's how one infers the presence of or the passage of gravitational wave. And if you want more information, you can look at the website of the LIGO collaboration, ligo.org, which basically has some very nice animations of how interferometry works, etc.
Yeah, I don't think any more questions are there. So, are gravitational wave frequent? Can you just?
So the gravitational wave, see, the point is any motion of massive object can produce gravitational waves. If I'm moving my hand, I can produce gravitational wave. But the problem is that they are too weak to be detectable using any conceivable technology. So, and using our current technology or even conceivable technology, if you want detectable gravitational waves, that has to involve really massive and compact objects like black holes, neutron stars, etc. And these phenomena happen, like collision of these black holes, etc., are not that frequent in the universe. For example, typically one binary merger happens in a galaxy once in a few million years. This means that your detectors have to be sensitive to a large volume in the universe, which involve billions of galaxies, so that once a year you can see, or you can see in a year you could see many gravitational signals. And this is what indeed is happening in LIGO. LIGO is able to detect gravitational wave collisions happening in up to thousands of megaparsecs, so thousands of or billions of light years away. So it basically, whatever happens in the local universe that has a volume of that has a radius of a few billion light years, LIGO can detect it, and that's how LIGO works.
I think we can take a last question. So there are a lot of questions coming up. Shajil UK, he has said that what are the other ways of detecting gravitational waves that you mentioned? Is there any other way?
Yeah, so the first technology that people have tried starting in the 1960s is what is called resonant bar detectors. Here the idea is that when gravitational wave pass through it, basically it hits everything that is on the way, right? So it produces a small hit on everything. And if you have an object like a tuning fork, it's a very precise frequency and it's a very sensitive, then, and if a signal of the same frequency goes through this tuning fork, then this fork would vibrate. And one could actually, looking at the vibration of this tuning fork, one could potentially measure the gravitational waves. And in the case of these resonant detectors, these tuning forks are like tons of very huge metallic objects of a few tons, like large aluminum bars. And that's one way of detecting. It's called resonant bar detectors. This is the first thing that people have tried, but not successful. A very active area of research currently using is called Pulsar timing arrays. And here the idea is that radio astronomers have been measuring radio pulses from what is called millisecond pulsars. These are very precise clocks. They have very precise rotation frequencies. They're much better than the best optical clocks that we have made on Earth. And when gravitational waves pass through our local universe, then essentially that would stretch the space, and that would cause a delay in the arrival time of radio pulses from a large number of pulsars simultaneously. And there is a large number of radio astronomers are using radio telescopes to probe such passage of gravitational waves, but again, it has not been successful yet. Another idea that is used by cosmologists is to look at the cosmic microwave background radiation. And if you look at the polarization of the cosmic microwave background radiation, then it should contain imprints of gravitational waves. So these are a few different things that have been around for several years, but now there are many new techniques have been proposed, but the viability of these techniques have to be yet demonstrated.
Okay. We'll take one more question. I think last somebody has said, what force can stop gravity in the black hole? I think
no force can stop gravity in a black hole. That's why it becomes a black hole.
Okay. So I think we will stop the questions now. And
Randy, I just want to add something.
Yeah.
Ajit, nice lecture. And actually, I know that whether you don't know, or we are having one gallery here on Astronomy, and it is going to be renovated in the next year or the next. We are planning to that one, and we are thinking to accompany this gravitational lensing and other new emerging technology. Those who are not aware of the not in any other gallery. So we are going to put this subject line there itself in the gallery. So I request you that if you have some, because we used to see these concepts and these phenomenal activities in an exhibit format, so that the visitor will come here, and the visitor ages, right? It is not like those graduation or something having astronomy they are related. Even their school children is also visiting here also. So if you be in contact, if you give some clues that how it can be arranged in a miniature form there in the exhibit, then it is also good for us.
Yeah, I'm happy to talk to you about that. When you have started working on it, I'm happy.
Yeah, I and also Jayanti from here also contact you regarding.
Sure.
Please help us too, so that it will be it's the frontier technology that is going on the gravitational and astronomy. That can be exhibited.
Sure. I'm happy to talk to you.
Thank you so much for this lecture.
You're welcome.
So formally, we thank Professor Ajit Parameswaran to have given a wonderful lecture, and all of us enjoyed the lecture. So thanks from the Regional Science Center and also from Public Outreach and Education Committee of ASI. So thank you. So
Thank you so much.
Thank you. Bye-bye.
Thank you. Bye.